Hello, welcome to this session of basic course in astronomy, Introduction to Stars. I would request Professor Sarita to start the lecture.
Thank you and good morning, everybody. So we are now in week 6 and I'm glad to see you all have come with me to this far to understand more about stars. So let us proceed with today's lectures. So if let us begin with a recap of what we did in the last week. We discussed about the stellar spectra, both the continuum and the lines, the spectral lines. The continuum can be approximated by a black body function. We have discussed what a black body radiation is and how it can be approximated by a Planck function or the black body function. Then the laws associated with black bodies, the Wien's law and the Stefan-Boltzmann law. And this for the spectra of the stars, we see that the continuum can be approximated by the Planck function, but this is the continuum not from the very interior or core of the star, but from the photosphere. In the interior, the temperature is very high, so even if the radiation that is coming from there, the thermal radiation, can be approximated with a black body whose temperature corresponds to the temperature there. As we are moving out, the temperature is decreasing, so at that radius, if one sees what the black body function or what the spectrum of the star would be, the continuum could be approximated to a black body function at that temperature from where we are measuring the radiation. Therefore, the spectrum that we are measuring of stars is from the photosphere, where the photons are coming, and superposed on these are spectral absorption lines, which are from very dense very less dense gas or cool gas that is outside, because in the case of the stars we cannot define a cutoff. It's like the density is there, and beyond some time the density decreases drastically. Okay, so those where the density decreases to very low values, the gas there is very cool, and that leads to the absorption lines. Okay, so we have also seen the classification of spectra based on the spectral lines that are observed, because this can be characterized based on the surface temperature, because the pattern of spectral lines that you see can be related to the surface temperature. And using these pattern of lines also, you can get surface temperature. So the surface temperature of stars can be obtained in two ways. One is by fitting the continuum of the stellar spectrum with a black body and seeing where the peak is by Wien's law. The other method of determining the stellar surface temperature is by looking at the pattern of the spectral lines. So let us go ahead. We had stopped with this. We will continue from there. So here are shown the spectral classification of stars. This is known as the Harvard Spectral Classification. So the Harvard Spectral Classification is the classification of stars based on surface temperature alone, using the pattern of spectral lines. So as we had discussed, on the left hand side, you will see the spectral types of the stars. You have the O stars, B stars, A stars, F stars, G stars, K stars, and M stars. So as you can see, the sun is a G2 type star, so its spectrum would be something similar to what you see in the G type star, but there will be a gradation. Now, on the x-axis, you have the wavelength, and of course here you have the surface temperature, or rather the stellar spectrum. And these represent, for example, the O6.5 star is, these stars are given names. So this is the name of this particular star, which is of spectral type O6.5. And we identify to be this O6.5 stars based on whatever spectral lines we see here. So this is the, as you can see, it is a lot of work to be able to note down these lines and come up with a theory to understand at what temperature these absorptions spectral lines will be seen corresponding to different elements. So the Harvard team, which is Annie Jump Cannon and group, they actually recorded few thousands or even tens of thousands of stellar spectra were already recorded. They actually noted down, analyzed, and tried to group them together. Okay, and the theory for this was later given by other people, and Saha played a very important role in this, because using Saha equation one can determine that at a certain temperature how many electrons of a particular species will be in a certain excited state, and you can use these kind of considerations and other considerations like Maxwell-Boltzmann distribution to or the Boltzmann distribution, to be able to tell how many, to be able to tell which lines, absorption lines you will see at which temperature corresponding to a certain species. When I say species, it could be atomic species, ionic species, and so on. Now, if one takes the surface composition of stars, we know that there are many, the composition is mostly hydrogen and helium, but there are also traces of heavy elements. So it was calculated. In fact, there was this lady, Cecilia Payen-Geperskin, who actually worked on this theory using the Saha equation and determined that using these spectra, actually, they determined the composition of stars and found that it is mostly hydrogen, and which was very unusual at that time, because they did not realize that you could have stars which are made of mostly hydrogen. They thought the composition would be very similar to what you see on Earth. Okay, so Saha equation played, our own Meghnad Saha, that Saha, he came up with this Saha equation. So the Saha equation played a very important role in determining what lines can be seen at what temperature. So as we saw earlier in the last week, I said that the A-type stars are very strong in hydrogen lines. So you can see these patterns of lines. This corresponds to the hydrogen lines. So the A-type stars are the strongest in the hydrogen absorption lines. And as you go towards higher temperature, the higher hydrogen absorption lines, that reduces. I mean, the strength of these lines reduces. The strength you can determine by seeing how dark it is with respect to the surrounding continuum. Okay, and here as you go even to the cooler side, it decreases. But then other lines, for example, start gaining strength. Okay, so using these considerations, using these considerations, one can determine the stellar effective temperature. As you know, effective temperature corresponds to the surface temperature. So currently astronomers use stellar spectra to determine the spectral type. Okay, and therefore the effective temperature or the surface temperature. So this again shows the stellar spectra. Here you can see this is an O7.5 star. There's also a V here. I'll come to this aspect shortly. And then this is a B-type star. This is A-type star. So here what you had seen was the spectrum as you would record it. This is the optical spectrum, and it would look like this if it has high spectral resolution. And now if you plot the intensity, like intensity is on the x-axis, you can say it is wavelength. On the y-axis, you can consider this as temperature. But the color or the intensity, that corresponds to the color corresponds to the intensity. So that is plotted here. Here the intensity is plotted as a function of wavelength, okay, for different spectral types. So this is an O7.5 star, this is a B5 star, this is a 2.5 star. So you know what these subclasses mean also. This is an F-type star, G-type star. We've discussed these subclasses earlier. Okay, now if we look at the hottest star, first let us look at the continuum, which we discussed earlier. The hottest ones will have continuum at shorter wavelength. Then as you start going towards the later spectral types, these hotter stars are called early spectral type. These are called later spectral type. This is just a terminology. It has nothing to do with evolution. One main sequence star cannot evolve to another type main sequence star. Okay, so this is something we need to keep in mind. So these hotter spectral types, I will call them hotter and cooler. As you can see, their peak wavelength, the wavelength at which the emission is maximum lies in the ultraviolet. And then as we go towards the cooler type, the wavelength at which the emission is maximum, that starts shifting to lower and to higher and higher wavelength, as we can see. And this is the continuum. This is with regards to continuum. Now, superposed on these are a number of spectral lines. We have also already seen what you mean by H alpha, H beta, H gamma lines. So these are the Balmer lines of hydrogen. As you can see, they are shown here. They are much more deeper in case of, as you can see from here itself, the strength is maximum in case of the A-type stars. For example, Vega is also an A-type star. Then you have the F-type star. And you can see that in case of the hotter stars, there are other lines like the helium lines. Are the excited states in helium also start getting filled up with electrons, and when they come down to the because of the higher surface temperature, the electrons in the helium are in the higher excited states, and even the helium ions are in the higher excited state. Helium is also ionized. The electrons in the helium ions are also in higher excited state because of the temperature effects, because of collisions, you can say. And then when they come down to the ground state, that is when emission would happen. But they get excited because of the collisions as well as by absorbing the radiation which is coming from the continuum or the photosphere of the star. So you will see this kind of a terminology, helium Roman 1, or for example, helium Roman 2, you may have, and so on. You may have Roman, here it is not there, but you may come across in astronomy sulfur Roman 4. That essentially means it's a third ionization, triply ionized sulfur. S4 means S3 plus. That means 3 electrons have been removed from the system. So when you say He1, that means it's neutral helium, and He Roman 2, which means helium plus. Okay, H1 of course is neutral hydrogen, and H2 Roman would mean ionized hydrogen, and ionized hydrogen are protons, as you know. So this is a terminology which is commonly used in astronomy. So if you come encounter this, it actually tells you about the ionization stage of that particular element. Now let us look at what are the characteristics of these different spectral types. And these, of course, let me tell you, these are the characteristics for not only the main, any type of stars which have these surface temperatures. So if for the spectral type O, it will appear bluish in color, and its surface temperature can range from 25,000 to 50 to 60,000 Kelvin. And again, you can have subclasses within them, as we have already discussed. The prominent absorption lines are helium, ionized helium, helium, and hydrogen lines. Now, in B-type stars, this also appears bluish, and the surface temperature is between 11,000 to 25,000 kelvins, and this comprises of only neutral helium and hydrogen. And A is bluish white. This has strong hydrogen lines, and the surface temperature is 7,500 to 11,000 kelvins, and it has some ionized metals. There are certain metals which are ionized. When I say, as we have already discussed, metals mean any element heavier than hydrogen or helium. So for example, you can have calcium, you can have, as you can see here, some of the calcium, magnesium, titanium, all these lines can also be seen. Okay, so these metals are present, and you can see lines corresponding to these ionized metals. The F-type stars, the surface temperature is 6,000 to 7,500 Kelvin, and this is characterized by these ionized metals. Then you can have the G-type stars, which is the sun, which is yellowish white in color, surface temperature 5,000 to 6,000 Kelvin. And you know, for sun, it is 5,800, you can approximate it. And it comprises of ionized and neutral metal absorption lines mostly. Then when you come to the K-type spectral type, these stars appear orange in color. Their surface temperature is 3,500 to 5,000 Kelvin, and these comprise of neutral metals. When you come to the coolest stars, which is the M-type stars, these are reddish in color, and the surface temperature is around 2,800, 2,500 to 3,500 Kelvin. Then these the absorption lines are characteristic of neutral atoms, and you can also have some molecules like titanium oxide and so on, even CH probably. Now, this is some of you were, I remember some of the questions you people had asked was regarding surface temperature. How from the absorption lines we can determine surface temperature. I gave you a very qualitative idea through a brief description some time ago, that you can actually use the fact that whatever lines are seen, you can relate it to the physics we know through the Saha equation and the Boltzmann equation. You can use these to determine that at a certain temperature, which lines will be, because you already know the energy levels of different atomic species. So you can use these equations to calculate that at a surface, at a certain temperature, if you consider each and every species, to what are the absorption lines that it is that we can possibly see. So that for convenience is shown, for example, in a plot like this, where the x-axis indicates the surface temperature. So it's decreasing as you're going from the left to the right. As you can see here, on the top is on the bottom is the spectral type, and on top is the surface temperature. It goes from 50,000 to 3000 Kelvin. Now, this is a very interesting plot because it tells you which are the lines you will prominently see at what wavelength. For example, as I said, the hydrogen, if you remember, we had said that the A-type stars have the strongest hydrogen absorption lines. So this is evident from this curve. The hydrogen absorption is prominent at around, as you can see, if you are considering this is not a linear scale, but it will be roughly at, let us say, 9000 Kelvin or so. So at this temperature, you will see the strongest hydrogen absorption lines, and as you are going away to higher temperatures, then the higher hydrogen absorption line strength decreases. Similarly, as you're going to lower temperature also, it decreases. And similarly, not only for hydrogen, but all the species which are possibly there and which are seen, this is how the lines are observed. Okay, the pattern of lines. That means, for example, the magnesium 2 also, that when I say magnesium 2, it is singly ionized magnesium, or magnesium plus, as we have just discussed. This is silicon plus, this is silicon double plus, this is silicon 3 times plus. So here the temperatures are so high that this silicon gets triply ionized, doubly ionized, and you can see lines corresponding to them at these temperatures. You can see the helium 2 lines and you can see the helium 1 lines, but the strength of these lines is much lower. That's why as we saw in the last slide, for the O-type stars, it's mostly hydrogen, helium, and ionized helium. Yeah, these lines are also seen, but their intensity or strength is much lower. Similarly, magnesium 2 line is also there, strength is lower. As you go towards the cooler side, then the other species start playing an important role. For example, the ionized calcium, ionized iron, and this is neutral iron, and this is neutral calcium, and so on. So this calcium also shows a strong, for example, absorption lines, and the strength is maximum, as you can see, near the K-type star. So these are the using these strengths of lines, one can actually determine what is the surface temperature of stars. So this is a very accurate way of determining the surface temperatures of stars. So this classification of stars based on spectral lines and organized on the basis of surface temperature is known as the Harvard Spectral Classification. So this is again shown here. Now in the earlier case, they were not labeled, but now you can see that this is the surface temperature and this is the characteristic spectral type associated with such a surface temperature. And on the x-axis, you have the wavelength. And here they are actually, you can see that these lines are labeled. Now let us look at the hydrogen lines. So the hydrogen lines are the Balmer lines. So they are the H alpha, H beta, H gamma, H delta, and so on. So you see, where does the strength become maximum? The strength seems to become maximum around the A-type star, particularly close to the A0 type. That is true in hydrogen. Then you are having all the hydrogens, it is the same, correct? Now, let me see the calcium here. This is the calcium 2. You can see that the calcium 2 is very strong here. Here it is just beginning to develop, is very strong here. But you also start seeing a lot of other lines as you go to cooler stars, because here the surface temperature is so low that a lot of what you say, metals, and even there could be molecules formed, because this is a very cool surface, like a CN, as you can see, titanium oxide and so on, and MgH. So these, once you have molecules, then you have a lot of molecular levels associated with that, which could be vibrational and so on, rotational. You won't see vibrational, rotational. Mostly these will be electronic states. So you'll see a large number of lines associated with these molecules as you go towards the cooler spectral types. But once you start going towards the hotter spectral types, then you see that even hydrogen decreases, and you see mostly ionized helium, for example. If you have even a better spectrometer where you are, and a large telescope, then you should also be able to see the silicon absorption lines, as we have just seen. Now, let us look at some of the star catalogs, because just now I introduced some time ago, I said that there are stars with the name HD type. So it is good to know what are the usual or typical star catalogs which are generally used. And for example, because you will see star names associated with these catalogs. Catalogs is a listing of a star which is compiled by either one person or a group of people, and they would give some information about the stars in this catalog, which is the positions and other information. It could be spectral types, proper motions, parallax. Now you are all familiar with these terms, right? So all this will be listed in the catalogs. So first is the HD or the HDE. This is the Henry Draper catalog. Henry Draper was not, he was an amateur astronomer. He also had at that time, you can say he had a lot of money, but his passion was astronomy. So he, and actually his wife, Lady Draper, they used to sit at night continuously watching stars and taking their spectra. And these were it so happened actually that he passed away suddenly, and then his wife decided to what do you say, continue this work, because her husband was very interested in stars and taking spectra. So she decided to continue this work. So she actually, but she herself just helped her husband. She had some interest, so she gave a lot of wealth away to the Harvard group. In fact, the Harvard group, those lady computers that we have seen, that was all funded by Lady Draper. So she gave a lot of funding so that these stars can be classified, right? We were talking about the classification in a proper way. So all that funding came from this Draper organization, which was Lady Draper. And when the catalog was fully made, they called it the Henry Draper catalog. So this is the catalog we are talking about just now, in some sense, the classification. So this was the first large-scale attempt to catalog stars. This was in the early 20th century, that is between 1918 to 1924. And this has stars up to a faint level of 9 to 10th magnitude. When I say this means apparent magnitude. Unless I explicitly mention, it will mean apparent magnitude. So this has classification of stars. This lists stars up to 9th or 10th magnitude, and it gives the spectral types, based on the surface temperature, as we have just discussed. And this was compiled by Annie Cannon-Jump and her colleagues at Harvard. But there are a number of other catalogs over time, and I've just listed some of them. There are others as well. So then there is the Bright Star catalog, which was compiled at Yale in 1930. This has stars brighter than visual magnitude 6.5. That means they are really, really bright. Okay, but this also contains other photometric data. Because you know that we can see up to magnitude 6. So this contains stars only up to 6.5 magnitude, but it is a good compilation because you can see all the stars which are listed there in one place together. But other than photometric data, it has also other information, like it has proper motions. Proper motion is also there. Okay, and the spectral types are also given. So when I say photometric data, that means in different filters, what is the magnitude that is given, the proper motions are given, and what is the spectral type. When, as you know, the spectral type reflects the surface temperature. Then there is the Smithsonian Astrophysical Observatory Star Catalog, that is known as SAO. So if you're in that, the stars will be given numbers, right? Because it's a catalog, a large number. So if you see SAO 35462, that means it is from this catalog, that is the entry number of that star. And this was compiled in 1966, and it has stars up to 9th magnitude whose proper motions are also noted very accurately. Then there is another very interesting catalog, or a very accurate catalog by the US Naval Observatory, that is known as the USNO catalog. Okay, and as you know, the name for the Navy, or when you are navigating, stars can really prove to be very useful in locating where you are, as we have seen much earlier. So this was compiled by the Naval Observatory, and it has positions, proper motions, and magnitudes in various optical filters for nearly 1 billion objects. Okay, and very accurately they are known. And it is down to a visual, that means you have stars up to very faint level, 21 magnitudes, and there are different versions as and when, because they need a large number of these stars. I mean, a large number of these stars are compiled, and over time, as they upgrade these catalogs, then you have different versions, B1, B2, C, and so on. We talked about Hipparchus catalog. As you know, Hipparchus was a satellite mission. We have already discussed this. And this catalog was published in 1997 and contains around 1 million stars with very accurate parallax measurements. And the latest one is the Gaia mission, which is still undergoing. And DR2 was released in April 2018, but you know, now DR3 is also released. The early DR3 catalog has been released in last December, and it has around more than, I think, 1 billion stars. So these catalogs are useful in understanding the properties of the stars. For example, the Gaia catalog, they just do photometric measurements. They take they don't take the spectra of stars. They don't disperse the light and take the spectra of many stars, but for some of them they have taken those, not all. Now, we have also seen Stellarium earlier, this software, and we know that this software is very useful to see what your night sky is in your location. Correct? I hope by now you have all installed and seen what your night sky looks like, and tried to see at different times of the year how the night sky changes. But other than that, it has a lot of information about the planets and other solar system objects and stars. Okay, so here, for example, shows the night sky. You can click on any of the star and you immediately get a lot of information about the star. For example, when I click one of the stars, this is what I had got. I'm just blowing this to show you what all information is there. I mean, it's amazing, because now you should be able to understand what this information is. So first is, what is this type of object? For example, this was the star that I clicked, and now I hope you understand these meanings. So HIP 84690 means this star is in the Hipparchus catalog, and this is the entry 84,690 in that catalog. This is also listed in the SAO catalog, which is the Smithsonian Astrophysical Observatory, and this is the number in that catalog, entry number. That means in serial number. Then this is also listed in the HD catalog, which is the Henry Draper catalog. So in the Henry Draper catalog, this is the entry number. Okay, 1,56,293. And what is this type of object? This is a star. So the same star may be there in different catalogs. And what is its magnitude? This is the apparent magnitude, is 5.75. I hope you now understand what absolute magnitude is. That is, if you bring the star to 10 parsec, what its magnitude would be. And then you see that it is 0.51. From apparent magnitude and absolute magnitude, you should be able to calculate the distance using the distance modulus, right? Assuming that there is no starlight getting absorbed. So that I hope you still recollect. M minus M equal to 5 log small m minus capital M, that is apparent magnitude minus absolute magnitude, is equal to 5 times logarithm of d in parsec to the base, that's logarithm to the base 10 minus 5. Okay, so if I give the apparent magnitude and absolute magnitude, it should be possible for you to calculate the distance to a star. Then we can also get the color index B minus V. This also in some sense can give us, you can model and get the surface temperature of the star. This is the right ascension and the declination. Now you know what they are, the coordinates of the star, equatorial coordinates of the star. And these are given in hours, minutes, seconds. This is as we have discussed earlier, the declination is usually written in degrees, arc minutes, arc seconds. Okay, so this is on to in 2000. This would be the RA deck, and on the date at which you are seeing, the RA deck could be slightly different. As you can see here, there is some difference between these two measurements. We have not talked about the reasons for the change. We have said that in our case, we had mentioned that they will remain more or less constant, but there is some small change because of the precession about the Earth's axis itself. Okay, so the Earth's axis itself is precessing because of the effect of the sun and moon, and because of which there is a small change even in the equatorial coordinates over time. But this change is not very large. It's and one needs to, but astronomers, we need to worry about it. Okay, at a first level, when you are trying to observe, only if you're using only if you're using large telescopes, you need to worry about this change in position. Otherwise, it is not so important. Now you also know what the horizontal coordinates are, that is the azimuth and altitudes. So this is the azimuth of the star. You know how many degrees, arc minute, arc second, and this is the altitude of the star from the horizon. Correct. So azimuth is measured from north, right, towards the east. Then these are other coordinate systems which I have not talked about, the ecliptic, galactic, and we have not talked about, we have talked a bit about sidereal time and so on, but let's not go into this. Let us look at the other information. So its distance is also given, but you can also calculate its distance using these two, but distance is also given. This is 363 light years. That is, light from this star to us takes 363 years. So today, if I'm seeing the star, that means this star is what I am seeing now is what it looked like 363 years earlier. Okay, and this is a very interesting concept, because if you are actually seeing a galaxy through a telescope, for example, galaxies are nearly millions of light years away. So that means if you are seeing the galaxy today, the photons from those galaxy have been traveling for millions of years. So you will be seeing today the galaxy which was million years ago. But now it may not be like that. It may or may not be like that. If it is not like that, if some change has happened, you will only, if some change happens in the galaxy now, for example, you will be only be able to see after a million years. Okay. Anyway, coming back, that was an aside. That is true for very distant objects. Then this is the spectral type. Now, spectral type, I am sure now you are able to appreciate what the spectral type beam is. This is among the hotter stars, and this is a B9 subclass. V I will talk about. And then this is the parallax. So you also understand what parallax measurement means, because using parallax measurement, you can actually calculate again the distance to the star. So you can calculate distance to the star using parallax measurement. You can calculate distance to the star using this distance modulus, if you know the apparent and the absolute magnitude. Now, earlier we were discussing that how can you determine the absolute magnitude if you don't know the distance? You can determine the absolute magnitude by looking at what the effective temperature of the star is. If you know the effective temperature of the star, for example, and if you know its radius, you know its luminosity. So you don't really always need distance to be able to tell you what the luminosity is. You can also determine the luminosity if you know the effective temperature and the radius. With these two information, you can get the luminosity. From luminosity, you can get the absolute magnitude. You see, so if you from absolute magnitude, and if you measure the apparent magnitude, also you can get distance. So there are these two. The way to, if a distance is calculated by this method, where you calculate the absolute magnitude using the surface temperature and radius, and you calculate, you measure the magnitude of the star, and using these two, if you calculate the distance, that is known as spectrophotometric measurement. That is, you're using the measurements from star to determine its absolute magnitude. The other way to determine the distance to star is through parallax, which is already discussed earlier. Okay, so in the last class, there was some question towards the end about what is this hydrogen 21 centimeter line. I'm sure many of you have come across this. First and foremost, it is important to know that this line is not related to stars. This line is related to gas. Okay, it is not related to stars. In stars, you will not see this line. Now, this in a hydrogen atom, we have seen this spectra, which is the Lyman series, Balmer series, Bastian series, and so on. Now, when I say 21 centimeter, where does this 21 centimeter come in? All of these are much higher in energy. So 21 centimeters is the wavelength of a spectral line of the hydrogen atom. But all these energy levels are very different. So this 21 centimeter is related to the hyperfine lines between the two levels of the ground state. Okay, so the ground state of hydrogen is actually not one state, it is made up of two states. Okay, this is known as the hydrogen hyperfine structure. And this two states, of course, some of you have just studied hydrogen atom, you may not know this. Over time, as you progress in physics, you will understand that there are various effects because of which the lines are not exactly just one, it can be composed of more than one lines. So when you look at this ground state, it is made up of these two levels. And what gives rise to these two levels? These two levels, it gives rise because of the interaction of the electron spin with the proton spin. So if the electron spin and proton spins are parallel, then this is the energy level of the ground state. It will be in this. And if they are anti-parallel in the opposite direction, then it gives rise to this. The difference between these two energy levels is very small, as you can see, compared to these. It's like million times smaller. 5.9 10 power minus 6 eV. This energy corresponds to 420 megahertz because equal to h nu, or hc by lambda, if you calculate, that corresponds to 21 centimeter. So in the ground state, it is made up of two levels, and these two levels, when the transition happens of the electron between these two levels, okay, for example, if there's a change of spin like this, then it gives rise to radiation, and that radiation has very long wavelength in the radio of 21 centimeter. Now, these kind of transitions do not happen in stars because this is very little energy. It won't matter at all. Usually in stars, you have transitions, much more energies are there, and you really have electronic transitions. But this is known as hyperfine because it is these levels are because of the interaction of the nucleus with the electron. So this kind of little energy is provided if there is a lot of hydrogen gas which is present, and most of the atoms are in ground state. Let us say the gas is very cool. Most of the atoms are in ground state, means the electrons of the atoms are in the ground state. Suppose I give a teeny bit of energy. Suppose one other atom comes and hits this atom, or because it has some energy, because of some very little temperature, it gives it a kick. Then it can move from this lower energy state to the upper hyperfine structure. And when it comes down, it can actually give off this photon, 21 centimeter photon. Okay, so this is therefore seen in very cool gas, not very cool gas, but cool gas itself in hydrogen. And this is used to find out, this is, since it is in radio wavelength, it does not get absorbed very easily by other gas, by the other particles which are there in the medium, called interstellar dust. It does not get absorbed, and therefore this is a very useful probe to find out where there is hydrogen gas, okay, in the universe. So this is known as the atomic hydrogen 21 centimeter line. For example, when the astronomers used radio telescopes to look at the sky, they had seen that in the sky, that there is this is along the galactic plane. Okay, this is shifted. Of course, the sky will be very different for different locations, but they have made a sky map where horizontally whatever you see is the plane of our galaxy, Okay, and in this galactic plane, most of the, as you can see, most of the hydrogen is in the disk, because we saw that most of the stars are in the disk, most of the gas is in the disk. So they have actually mapped the galaxy and seen where most of the hydrogen is, and this is the direction where the galactic center is. And this is like something that closes, you know, because it's a sphere, so it is something like that closes. So it's like an orange. If you open, you can't really make it flat, but they have made it flat using some projection techniques. Okay, so you can just take it like that. So this is like, open it up, it's like atlas, you know, when you see it, you're seeing it flat, the maps, but actually the earth is round. But you will see that even for earth, very often they either put a rectangular kind of projection or this kind of projection. So towards the center is where the center of our galaxy is, and this is the opposite direction. Okay, away in the opposite direction to the galactic center. So it essentially closes in this direction. So this shows that there's a lot of hydrogen gas associated with in our galaxy in the disk. Okay. Okay, now let us move at some of the other properties of stars. Let's come back to stars and try to understand what are the other measured properties of the stars and how we can determine some very important characteristics of stars. Till now, we have tried to see the brightness and the radiation coming from stars. But can we also find out other properties of stars? For example, we said we need radius. We need radius to determine luminosity, or if we know luminosity, we can determine radius. Is there some way to determine, for example, or get an estimate of the radius of the star? Okay, so we'll look at some of these properties. As we can see, luminosity, two very fundamental properties of the star are the luminosity and the effective temperature. So what is the luminosity? Luminosity is the total energy given off by the star per unit time. We have discussed this earlier. And you can also write it in terms of absolute magnitude, where absolute magnitude is related to the negative logarithm of the luminosity. The other characteristic is the effective temperature, which is the surface black body temperature of the star. These are very two important observables of the star. So surface temperature you can determine independently. As we have seen, there are two methods to determine surface temperature. One is by using Wien's law, other is by using the pattern of the spectral lines. You can, whatever pattern you see, you can relate it to the template of the different pattern of stars that I have showed you and try to see which it matches the most. That is the way to do it. And luminosity of a star, if you want to determine, then you need to know the distance to a star. And if you want to determine it independently, you need to know the distance to a star. You need to know the flux to the flux of the star. That means the brightness, measured brightness. So the luminosity you can determine in this way, where you have which is can be written as 4 pi d square times f or b. Here it is written b as brightness, but it can be the flux. Flux and brightness in this case are the same. So luminosity is 4 pi d square f, and we also know how to relate the surface temperature to the luminosity. So that is using the black body relation, the Stephen Boltzmann law. You have the surface area of a sphere multiplied with the power emitted per unit area of the black body. So the sigma T effective power 4 into 4 pi r square, that is also the luminosity of a star. Now, if I want to measure, so I will measure surface temperature in one way, and I will measure luminosity by measuring total brightness of star. And let us say these are two different quantities of the star. They are related. There is some relation. We'll come to that. But we don't know this. We don't know radius of star, because when you look at a star, all the stars appear as point-like. You do not know what the radii are. So people were very curious. Let me see, if I plot luminosity versus effective temperature, what do I get? Will the entire LT plane be occupied? L is luminosity, T is effective temperature. So if I plot luminosity and effective temperature of all the stars I see in the sky, or as many stars whose distance I know, because only if I know distance, I can get the luminosity. So if I know the luminosities of a large number of stars, if I know their surface temperature from the spectra, then I will plot them. So I will try to see where they lie in the LT plot, because that is going to give me really a lot of information about stars. Okay, as we will see how. Because if it is lying everywhere, that means you can have all possible radii and all possible surface temperature. But if it is not, then it means that there is something which is constraining the radii or the surface temperature. So the question remains is can the stars occupy the full LT plane? So this experiment was done very early on, as you know, early in the 20th century when they started measuring the effective temperatures of the stars. And they knew the parallaxes of some of these stars, so they knew the distances, so they could calculate the luminosity. So this was done by two astronomers. There was a Danish astronomer called Hertzsprung. In 1905, he gave a table of the luminosity and the effective temperature of a random group of stars. Okay, and the similar thing was given by Russell in 1914, but he made a plot of it. Okay, and how did both of and how did the plot look like? The plot on the x-axis had the surface temperature in the inverse scale. As you know, where we have discussed earlier, that surface temperature can be related to the color index. Color index is the difference in magnitudes through two filters, u minus b, b minus v, apparent magnitudes. Okay, apparent or absolute, it doesn't matter, because when you do the color index, the distance effect gets cancelled out. Then on the y-axis was the luminosity or the absolute magnitude. Okay. Okay, so if you are plotting in the absolute magnitude, then of course it will come in inverse scale, and if you are plotting in luminosity, you will see that it goes up. So this was the first plot which was made of the luminosity versus effective temperature. This is known as, because it was done by these two scientists, astronomers, it is known as the HertzgramRussell diagram. Okay, so on the x-axis is the surface temperature in inverse scale. Here you can see only the spectral types are marked in inverse scale, and that relates to the surface temperature. Inverse scale means as we are going from right to left, the temperature is increasing. You say, I don't like that, I want to go the other way around. You can do, but generally the norm among astronomy, because of this earlier plot, was to do it in the following way, that you have the hottest stars here, and then you go towards the cooler stars as you go towards the right hand side. Now, in terms of luminosity, luminosity increases from top to bottom, and absolute magnitude is an inverse scale. So the numbering wise, it has a larger positive numbers lower and negative numbers up. And yes, so the important thing is now what did they find? They took a random group of stars and they found that, okay, it should be more or less uniformly distributed, but they did not find that. What they found was that most of the stars were distributed in a band which runs diagonally across this LT plane. Okay, and there were some stars which were lying here, and some stars were there here, a little bit stars were there here, but most of the stars lies here. Why is it that most of the stars lie here? And that is where the story of the stars, in terms of understanding internal structure, energy generation, energy production, all this is related to this, because these are ultimately the observable properties of stars. We cannot see the interior of stars, as you know. All that we know about stars is from the surface, and yet it is amazing that with a graph like this we will be able to tell a lot about stars. As we will proceed, you will understand what I mean. So this, suppose I take the Hipparchus. Now you know that Hipparchus actually was a satellite mission, took a large number of stars, very accurately, precisely. It measured the surface temperature, and it measured photometry in the sense it measured the flux through different filters. But if you subtract the magnitudes through two different filters, it is a proxy or it is analogous to the surface temperature. You can relate it to surface temperature. Okay, so if you do this exercise and you plot the absolute magnitude for a large group of close by stars, they found the pattern is something like this. Again, it is not filled up. Most of the stars seem to lie in a diagonal band. There are some stars up here and there are some stars here. Okay, so it is very interesting to note that there is a certain pattern of the luminosity and the surface temperature. There is a relation. Now we all know what is the relation between luminosity and effective temperature, isn't it? So I'll come back to this. We all know the relation between luminosity and effective temperature. It is related with radius. So L is equal to 4 pi r square sigma T power 4. Now, if I keep r constant, If I keep r constant, what happens? L is equal to constant times t power 4. So for different values of r constant, I will plot that L proportional to t power 4. I will draw that, and you will find that it goes as a line with a power law index of 4. Correct? Luminosity is proportional to t power 4. This is log-log plot, so it is a straight line with slope of 4. Now, this is for different radii. Okay, so you have something at a 0.01 solar radius, the line would be something like this. Luminosity and effective temperature will be related like this. Then this is a schematic thing. So 0.1 solar radius, this is what it is. 1 solar radius, you see something like this. 10 solar radius, you see something like this, and so on. So this is how you see. Now over this, I tried to see where my stars were. As I said, this is schematic. Most of the stars seem to have this kind of lie on a diagonal band like this. Okay, then there are some stars which are here, and there are some stars which are here. Essentially on the x-axis, you know, the effective temperature. Essentially, what does it mean? Essentially, it means that for a certain effective temperature, all possible values of r may not be possible. Their nature only allows us some values of r. Okay, so this is most of the stars are here. We identify that most of the this band corresponds to the main sequence. Most of the stars are here. So this is the main sequence band. As I've already said earlier, the star spends most of its lifetime in the main sequence phase. So therefore, statistically, if you take a random group of stars, most of them will be in main sequence. So these are the main sequence stars. But there are some stars which have the same effective temperature as my main sequence stars, but they have much larger radii. Okay. On the other hand, there could be some stars which have the same effective temperature or surface temperature as main sequence star, but they have very small radii. So they decided to call these stars as giant stars because they have much larger radii. They can have same effective temperature, but radius is much larger. Now, because the radius is very large, the luminosity will be very large, isn't it? And similarly, in the opposite sense, if you are having very small radius, then what happens? Your luminosity also becomes very small. So these objects, but the surface, they are seem to lie towards the higher surface temperature side. That's why these were called white dwarfs. These were called red giants because they were, many of them were towards the cooler side, towards the reddish side, and they had larger radius. So they are the red giants or giants, and these are the white dwarf stars. So this is what this is shown here. This is the HertzgramRussell diagram. You see the temperature goes in the inverse scale, increasing from left to right, and the luminosity is increasing from the top to bottom. Most of the stars lie in the main sequence band. There are some stars which are lying here towards the reds. They are the giants. And then you have some dwarf stars because they have much smaller radius. So you see, this already is giving us, starting to give us very interesting information that you are having stars lying in this band. Then you have some giants, you have dwarfs. Okay, and the other, why are there no stars present in the other regions? Because the way because of the physics and how energy is getting energy generated interior is getting transferred outside depends on many factors, and because of those factors, it does not allow the star to have any arbitrary radius. Okay, any arbitrary radius you cannot have. This is related to the energy generation and the physics of energy transfer within the stars, because ultimately the energy that we are seeing and the surface temperature is related to how energy is being transferred from the interior to the surface. Okay, so you see, we have already grouped stars into different categories. Main sequence stars are those which are fusing hydrogen to helium in the cores. Then you have certain giant type objects, you have certain white dwarf type objects. Just based on the observed surface properties. We are not talking about evolution, we are not talking about anything. We are just trying to see, as our thought process evolved, how our understanding has improved. So from a purely observational diagram, we are able to categorize stars into these different classes. Okay, So as I said, the stars which lie along the diagonal band are the main sequence stars. Stars above the main sequence could have the same effective temperature, but they are much more luminous and have much larger radii. These are the giant stars. Then you have stars which are lying below the main sequence band. They have much smaller radii, but could have same effective temperature or larger. These are known as white dwarf stars. Okay, and obviously you know that if we know that, suppose you are able to measure the luminosity of a star and you know its effective temperature, you can calculate its radius, isn't it? You know the effective temperature, you know the luminosity, you can calculate its radius, and therefore you can determine whether it's a giant type star or whether it is a main sequence star, where it is lying. Based on this plot HR diagram, you can immediately tell that whether it is a giant type star, whether it's a main sequence star, or it is a white dwarf star. Okay, so because now for the same, earlier we saw that the spectral classification was done based on the surface temperature, but now we are seeing even if you are having same surface temperature, you can have categories of different kind, main sequence, giants, and so on based on where they lie in the HR diagram. Okay, so because of this, it was decided to again have another classification scheme, which is known as the luminosity class, because it may have same effective temperature, but because radius is different, its luminosity could be different. Okay, and that is known as the luminosity classes. Here, for example, is shown HR diagram with some of the prominent stars that we know. Okay, for example, Betelgeuse, as you can immediately see and recognize, right? Betelgeuse is here. It is between a KM type star. Okay, and it's very luminous, right? And then you have these are the supergiants. These are giants. There is Aldebaran. There is Deneb, and then you have, and these are, of course, you know, these, the sun is main sequence, Sirius. The bright Sirius, which you know, is actually not a single star, it is a binary star. The brighter component which you can see in your naked eye, the brightest star in the night sky, that's the Sirius A. Okay, and that is a main sequence star, but it has a very, very faint in optical bands companion known as Sirius B. Now if your eyes could detect x-rays, for example, suddenly you switched off or pressed a button that your eye, instead of seeing optical, decided to see x-rays, you know what you would see? You would see that Sirius A is very not visible at all, and Sirius B becomes very bright. So it so happens that Sirius B is very bright in X-rays and Sirius A is very faint in X-rays. So you can immediately tell that the surface temperature of Sirius B is much larger, right? It is actually a white dwarf star. Okay, so Sirius B is a white dwarf star, binary companion to Sirius A. Then you know, must have heard of Spica and Proxima Centauri. You can see the stars with some of the stars which you know where they lie in this HR diagram. Okay, what we will do now, we will come back and continue the luminosity classes. Let's take a break of 5 minutes. After that, we will be back. Okay. Okay, so welcome back. So we were talking about these luminosity classes, right? I mean, how do we know that classification, spectral classification on the basis of just surface temperature is not enough, because in the Hertzsprung-Russell diagram, you see that there are stars which can have similar surface temperature but can have very different luminosities. So this Hertzsprung-Russell diagram is also known as HR diagram. So I will be referring to it as HR diagram. So as you can see, the stars on the HR diagram, they can be of different types. You can have giants and you can have white dwarfs. That is based on the size of the star, and using that luminosity, you can also, and the effective temperature, you can estimate what its exact size will be. Okay, and the main reason being that stars with the same effective temperature can have a widely varying luminosities because of different sizes. Okay, so here these are the luminosity classes of the stars. The luminosity classes are 0, 1a, 0, Roman numbers 0, 1, 2, 3, 4, 5, 6, and 7. Okay, so this is how the classification or luminosity classification of stars is. So usually when we are talking about spectral classification, we give the Harvard spectral classification, plus we also give the Roman letter associated with the luminosity classification. This classification of the stars is was done by a group, Morgan and Keenan, and they did it at Yerkes. So it's known as Yerkes luminosity classification, unlike the one which was done on the basis of surface temperature by Annie Jump Cannon at Harvard. So that's known as Harvard classification. This is known as Yerkes luminosity classification. That's Harvard spectral classification. This is Yerkes luminosity classification. So just to reiterate, these very stars which have a lot of luminosity and large radius, they can have a large range of temperature also. These are extremely luminous, and these are extremely luminous supergiants. They are known as hypergiants. So the 1a and 0 belong to this class. Then you can have 1a, you can have some 1a. As you can see, it's no, most of the stars are not just here. You can have some stars here. Now this represents a kind of subdivision. Okay, that this is supergiants. The generally bright giants will lie here. It does not mean that it is not fully filled here. You can have some stars which are kind of, you may find it difficult to distinguish between supergiants and bright giants. Then it's okay to say that we think it is 1b to 2 and so on. So 1a are the luminous supergiants, 1b are the less luminous supergiants based on the absolute magnitude in V band. This is how they are classified. Then you have the bright giants, which is luminosity class 2, Roman letter. Then you have the giants, you have the subgiants, and you have the main sequence star. So the main sequence star is this 5, also represented as V. So now you understand that in the Stellarium, we looked at the star that was B9V. The moment you see V, you should understand it's a main sequence star. It is also known as dwarf, because compared to these other giants, its radius is relatively smaller. That's why main sequence stars are also known as dwarf stars. This is different from white dwarf. White dwarf are objects which have very low radii. So if it just dwarf is mentioned, it means it's a main sequence star. If white dwarf is mentioned, that means it belongs to this category. Then below the main sequence stars, sometimes you can have stars which seem to lie below the main sequence. These are known as the sub-dwarfs. Then you have the white dwarf stars, which are lying here. So we have identified the luminosity classification. We have identified the effective temperature spectral classification. But what are these stars? What is internally, what happens in all these stars? As we will see, this is related to, for example, this is related to how the energy is transferred interior to outside, and during which stages does the star pass through the giant phase, dwarf. We have touched upon it in the very first lecture, but we will be talking about it soon to understand. Okay, and this objects which are not stars, that means they do not have enough. When do you call something a star? Nuclear fusion, hydrogen to helium should happen in the core. Okay, but if that does not happen, then these are known as brown dwarfs or red dwarfs. There is some nuclear fusion, but it is not hydrogen to helium, it is deuterium fusion. A little bit happens, or can happen in these kind of objects which are known as brown dwarfs. People are now also investigating brown dwarfs in detail, and they have also given it a spectral class, L and T. L and T spectral classes are assigned to brown dwarfs, but we will not be going into details of brown dwarfs here. Now, where does the sun lie? Sun is a G2V type of stars. G2V. Now you know, I had earlier said it's a G2 subclass. So the 2 is the spectral class, Harvard spectral class, and V means it's a dwarf star or a main sequence star, and this is according to the Yerkes luminosity classification. So a star, when it is given, its spectral classification is given. We usually give the Harvard spectral classification as well as the Yerkes luminosity classification. And that with that, you can immediately locate where it would be in the HR diagram. Okay. Okay. So before we move away from this topic of luminosity classes, let us look at the fact that the giants, the stars, the radii are much larger, right? So once you have very large radius, what happens to but the mass may be the same or may not be the same. Suppose the mass is, let us say, mass of the star itself becomes a giant star. As we have seen in the stellar evolution, this is possible. So what happens? What happens? The mass may remain the same. Let us assume there's no mass loss. Mass is the same, but its size has increased. Then what happens to its surface gravity? Its surface gravity is now going to decrease because its radius is much larger. So we know where you define surface gravity on Earth. Similarly, you can define surface gravities of stars. It is a measure of the size of the star and its mass. In other sense, it is a measure of how compact it is. Not exactly density, because density will be mass by r cube. This is not density. This is a measure of the compactness of the stars and gives an idea of how much surface gravity is there. So, for example, the surface gravity values, typical surface gravity values of main sequence stars. I will give an example of a giant, a white dwarf, and a main sequence. So, for the sun, the surface gravity is of the order of 4.4. And in astronomy, the way we define surface gravity is by using this logarithm of quantities, log g is equal to log of g m by r square. So when I say surface gravity, it is the logarithm of g. Okay, and that is why, as you can see, it will be 4.4 for the sun. Okay, this is a logarithm of this value. Okay, and if you compare with Sirius B, which is a white dwarf, then its surface gravity, it is a very compact star. So it's a very high surface gravity. Its radius is small. Compared to the mass, the radius is really very small. That's why we call it a compact object. So this is a white dwarf star. White dwarf stars are very compact object, and they have high surface gravities because their radii are very small. And then if you look at Betelgeuse, for compact objects, as you can understand, the surface gravity values will be higher. Now, if you look at Betelgeuse, for example, this is giant star. What happens? The R becomes very large. Then what happens to surface G value? Surface gravity, the log G value decreases. So as you can see, it is minus 0.6 in case of Betelgeuse, which is a supergiant. Okay. That also is an indication about what the class of star the star belongs. So if it has very high surface gravity, that means it's a compact object. For example, it's a white dwarf, or it has a low surface gravity, means then it is a giant type object. Its radius is very large, and so on. But this is a physical quantity. It relates the mass of the star to the radius. G, of course, you know, is the capital G is the gravitational constant, and small g is the surface gravity here. And usually for stars, again to reiterate, we write it in terms of logarithm of g. So now let us look at the general properties of the different star classes. Now we know what are main sequence stars to some extent, at least their properties. And let us look at other properties, okay, like giant stars, white dwarf stars, and superstars. supergiant stars. So if in the main sequence stars, we have already seen how the spectral type, how the surface temperature changes, how the radius change, how the radius is for different main sequence stars. Then for how the mass is for different types of main sequence stars, the luminosity, and the lifetime. Lifetime means how long the star spends in the main sequence phase. This is not something we have seen earlier, but if you can see here, immediately you know that the most massive stars, they have the shortest lifetime. It goes inversely, but inverse in some power law form. We will come to that aspect also. Can we determine the lifetime of a star if I know its mass? Yes, it is possible. Again, this is based on observations. Okay, and abundance means the composition. So we will, abundance means not the composition here. Abundance means how, suppose you take a random group of stars, how often you will find O type stars, how often you will find red type stars. And from this you can immediately see that the low mass stars are much more common than the high mass stars. So we will be touching about some of these aspects as we move along, the various properties, how the properties change with mass and so on. Now let us look at the giant stars. As you know, giant stars are usually low mass stars. These are stars near the end of their lives. Beyond the main sequence evolution, you will come across giant stars. Okay, and their spectral types are mainly G, K, and M. Okay, and the surface temperature varies from 3000 to 10,000 Kelvin. The radius is 10 to 50 times the radius of the sun. Mass is 1 to 5 times sun. Luminosity is 50 to 1000 times that of the sun. And lifetime is about 1000 million years. If I look at white dwarf stars, these are the dying remnant of low mass stars. They have a spectral, although we have not characterized a spectral type beyond O, but white dwarfs can have surface temperatures which are higher than the main sequence spectral type O. So white dwarfs generally are given a separate spectral classification of the type D. Okay, and the temperatures are usually under 80,000 Kelvin. This is the upper limit, and the radius is much smaller. Okay, for example, 1% of the sun, and the mass is less than 1.4 times the mass of the sun. Then the luminosity, they are very, very low luminous because of the small radius. Okay, there's no question of lifetime here because these are not undergoing nuclear fusion. So these are just hot objects which are just cooling off. So they will remain like that. Now, if you look at the supergiant stars, these are the high mass stars that will evolve beyond the main sequence phase to the supergiant phase. And they can be of all the spectral classification from O to M. Okay, and the surface temperature varies from 4000 to 40,000 Kelvin. The radius is around 30 to 500, and the mass can be so these are of course for the massive stars. They evolve in this to supergiant phase from 10 times to 70 times. This is the luminosity range. Lifetime is about 10 million years. Okay, so these are some of the broad characteristics of the different classes of stars that we have just talked about. Now, let us try to understand the properties of the stars more in terms of how they are formed, what the properties are there for the main sequence stars, and then how they evolve. Okay, so let us first begin with formation of stars. How are stars formed? Okay, so for that, if you look up at the night sky by now, I hope you are able to recognize this constellation. This is the Orion constellation, and we know that between the stars, the space is not really empty. Although it looks like it is empty, it's not really empty. It is there is some medium between the stars that is known as the interstellar medium. Now, the interstellar medium is made up of two components: the interstellar gas and interstellar. If I take a certain volume of the interstellar medium and by mass I measure how much mass of gas is there and how much mass of dust is there, then interstellar dust is usually 1% of the mass of the interstellar gas. Okay. And what is this interstellar gas? Interstellar gas composition we have anyway seen, right? Mostly it's hydrogen, helium, hydrogen around 75%, helium 23%, and then the rest can be heavy elements. Of course, that depends upon different parts can have different, for example, slightly different composition depending on whether enrichment has happened with the heavy metals or not. Now the question is, why would you look to an interstellar medium? Okay, I suddenly started talking about interstellar medium because this is the medium from which stars are born. That means stars are formed from the interstellar medium, okay, which seems to be very rare and so on. So that's the medium from which stars are formed, and that is the medium into which stars eject matter at the end of their lives. Okay, and all the bodies, planets, all the solar system bodies, everything that we know of is ultimately made of this interstellar medium. If you really went back in time to understand where did all this come from, everything has come from the interstellar medium. The star, the planets, we, for example, everything is from the interstellar medium. And interstellar gas composition, we have already seen this in some detail. This is the interstellar gas composition. Mostly it is hydrogen and some bit helium. And then you have even more smaller traces of other heavy elements or metals, oxygen, carbon, neon, and so on. And you maybe these as we have seen in the first lecture, all these heavy elements come from various processes in the stellar interiors. That means there are these fusion reactions occurring which are leading to the formation of these higher and higher elements, and then during the later stages of stellar evolution, layers or the matter which has been processed in the interior, that gets mixed with the interstellar medium. So the interstellar medium is continuously getting enriched because of the stellar processing that is happening. So if you are actually wondering, for example, how the silicon that we are seeing here on Earth has come from, or if you are even wondering the gold, that where it has come from, or any other element, then all this has actually been, if you want to go back in time, this has all been processed in some star, in the interior of star, that has gone into the interstellar medium from which the solar system formed, the star, sun formed from the same medium, and planets formed from the same medium. And then we ourselves as human beings, we have also come from here itself, right? So we are also formed, and all these elements which you see, right, platinum, rhodium, anything you see, that has actually been processed somewhere in the interior of some star. Now, what is this? This is about interstellar gas and the composition. But what is this interstellar dust? Okay, is it the same dust that we see around here? No, it is different. They are much, much smaller in size. So interstellar dust is made up of sub-micron sized particles. I mean, 0.01 to 0.3 micron. That is a range. And usually they say that the smaller sized particles are much more abundant than the larger sized grains. Even the smallest grains are less than a micron in size. That is what we anticipate. It's very interesting because we have not seen interstellar dust. The closest that we have seen to interstellar dust is interplanetary dust. Okay, there are missions which have taken this planetary, for example, dust, and we try to, so this is one such picture of this dust, as you can see. Now you may be curious that we have not seen this dust. We have seen only interplanetary dust. But what about interstellar dust? Yet we are saying that we know the size, we know the range, we know what it is made up of. How do we know this? It's really very interesting. We know this just from observations of the electromagnetic radiation. I'm not going into details, but just to give a brief idea, the star, the light that is coming towards us, because of this interstellar dust, it can get absorbed. And the way it gets absorbed, we use those properties to infer about the dust particles. Okay, because ultimately whatever absorption lines, whether you are seeing in the spectrum of stars or whether you are seeing absorption because of interstellar dust, they have unique fingerprints. These fingerprints are related to the composition of the atom or the dust. Okay, but atom and dust are different. Atoms, of course, are in gas phase, whereas dust is in solid phase. So they are different. They will show different signatures also. So the dust particles are usually made up of silicates, which is SiO2, and some carbonaceous compounds. because we see signatures of these we see spectral signatures of this composition. And it is also made up of some ices, for example, water, methane, and so on. And we anticipate that the structure of this interstellar dust should be something like this. In the center, you will have this small ice silicate core, silicate and graphite or carbonaceous core. And then but it doesn't mean other elements won't be there. It is expected that some amount of magnesium, some amount of iron, nickel, all these are expected to be there in this, are mixed along with the silicate and the carbon. But mostly it is expected to be silicate. And then this is supposed to be coated with ice. It is believed that there is a coating of ice, of water, methane, or whatever. But this ice can therefore, coating can be there in those dust particles where there is the interstellar medium is cold. Because if, for example, the dust particle is is at a distance from the star where the ice can sublimate, then you will not have the ice coating. If the dust particle is very close to a star, for example, then the silicate itself may get sublimated. So the dust particles may get destroyed very close to star, because the star gives off UV radiation. So very close to star, you will not expect dust to be present. This will be present in regions where the dust can be present. Okay. So these dust particles, they absorb and scatter light. This is known as extinction. And by looking at the interstellar extinction of a starlight, we can infer about the properties of these dust particles. Now, you may be wondering, then where are these dust particles themselves produced? And as of now, we believe that these dust particles are produced in the outer layers of very cool certain kind of giant stars known as asymptotic giant branch stars. We will be coming to what this asymptotic giant branch star is. It's a kind of giant star, but we will be talking about it later along the course. But for now, you can just assume it to be some kind of giant stars. And in the outer layers of these, oh, I don't have that slide. Okay, where I removed it. Okay. So in the outer layers of these giant stars, you can have dust particles getting formed. Now you'll say, how is dust particle getting formed? It so happens that these dust particles made up of silicates, they can form by sputtering in cool atmospheres where the silicate starts, the silicon that is present, they start to condense out. Okay, in sputtering environment in the outer layers of these stars. And that because the sublimation temperature is of the order of 2000 Kelvin. So there are conditions are present for these dust grains to be formed. How are we sure? Because we have seen AGP stars whose outer layers are all made up of this dust, you know, the signatures of this dust, and it's actually seems to be throwing out a lot of dust. So somehow dust is being formed in the outermost layers of these kind of giant stars. Now, the interstellar medium is not the same everywhere. Homogeneous means it's not at the same density everywhere, nor is it static. That means with respect to time also it is changing. Today, if the interstellar medium is very cold, and then, for example, let us say a star is born close to it, then after a few millions of years, because of radiation from the star, the interstellar medium is bound to change here. So interstellar medium as such is a medium which is neither static nor homogeneous. Okay, at different locations in space, it can have different densities, temperatures, and so on. And based on these characteristics, the interstellar medium is broadly categorized into three phases. Okay, atomic interstellar medium, molecular interstellar medium phase, and ionized phases. And these phases are the molecular, atomic, and ionized, is based on what form, since hydrogen is the main gaseous component of the interstellar medium, in what form hydrogen is, that decides that broad interstellar medium phase. So if the gas is very cold, the hydrogen will be in molecular form. So then it is known as a molecular phase of the interstellar medium. But if the gas, for example, is at a temperature where atoms are not in molecular form or ionized form, they are in atomic form, then we call the atomic phase of the interstellar medium. Then we can also have interstellar medium close to the star, where the dust may be sublimated and even the gas is ionized. You cannot get rid of the gas becomes ionized. So that's the ionized phase of hydrogen. When I say gas is ionized, hydrogen could be ionized. When hydrogen is ionized, it's known as the ionized phase of the interstellar medium. So you can have interstellar medium, you can have different phases depending on their temperature and their density. Okay, so the most densest of these is when the medium is cold. Correct. We all know that how the ideal gas laws would be, right? If it is very cold, it will be dense. If it is hot, it starts expanding. That means density decreases. Okay, so all those thermodynamics comes into picture even in the interstellar medium. And when it's in very high ionized gas phase, then the density starts becoming very less because it tends to expand. Okay, so of these various phases, if we want to understand star formation, we have to go and understand the most densest phase, which is the molecular phase. So when these are known as the molecular clouds. So the star formation occurs in the molecular cloud phase of the interstellar medium. So here, for example, you can see this is a picture taken by Hubble Space Telescope. There is a lot of stars. There's a lot of radiation being given by stars, but these pillars which seem to be standing up, this is actually very dense cloud. So this background radiation, you can see it's coming from the side, but here it is getting blocked because of the dust which is present there. That's absorbing and scattering the light, so you can't see it. And the medium is very dense here. It's not the gas which is absorbing most of this. Gas can also absorb, but it is the dust which has a more drastic effect on the starlight. So these, as you can see, are the molecular phases of the interstellar medium or the molecular clouds. And it is within these dense clouds that star formation occurs. Okay. So where do stars form? And stars form in the molecular cloud phase of the interstellar medium. Now let us proceed to understanding a little bit about star formation. Star formation by itself is a very elaborate process. I will not be going into those details. There are a lot of research going on, try to understanding the exact sequence of events leading to star formation process. But what we will be doing is just understanding in a rudimentary way what are the main things which lead to the formation of a star. So as I have said, the interstellar medium can be in different phases. You can have the dense cloud, you can have the diffuse cloud, and then you can have the warm ionized medium. This is the hot medium, and so on. So there are different phases. And this is the AGP stars where the dust is produced. That also mixes with the interstellar medium, and that's how the dust gets mixed with the interstellar medium. And it is from this interstellar medium that stars are formed. Okay, and again after the end of the life cycle of the stars, it will again give off material to the interstellar medium itself. Okay, so all this activity is happening out there in space. Okay, but of course on time scales which are much slower than what our lifetimes and what we have been observing. Okay, so I will just show you some molecular clouds, and here you can see that if you see dense blobs or globules like this, these are not some holes to another universe or not pathways to another universe. These are essentially molecular clouds which are dense phase of the interstellar medium. Okay, so, and for example, what you see here is a cloud on the left hand side is a cloud called the Barnard 64. Now somebody can easily say, oh look, this looks like a hole, a black hole or whatnot, but no, it is not. How do you know? Because if you take the same image at longer and longer wavelength, the dust absorption starts getting reduced and you can begin to see the background stars. Okay, so this is mainly because of extinction of light, the absorption of light by the dust which is present here. Dust absorbs at shorter wavelengths more than the longer wavelengths. So you will see that it appears to be very dark here. Similarly, this is the Eagle Nebula, and this is the background radiation from different stars, but you can immediately see that there is some dense cloud here. And these are the molecular clouds, and it is within these molecular clouds that the conditions are good enough for the star formation to occur. Now, how is a star formed? Okay, let us look at the process of star formation. This is, of course, a cloud where stars are being formed. As you can see here, these are stars which are being formed here. Now, let us look at the process of star formation itself. We know, all of you know that the force due to two masses, gravitational force due to two masses, is given by this expression. Now, what is the potential energy associated with this force? The potential energy is given as negative integral of the force, and you can write the potential energy. If you want to write in this form, it will become minus g m1 m2 by r. So it has an inverse relation with the distance between 2 point masses. Now this is of course when you have two different point masses. So we will come to the case when you have a continuous distribution, but suppose you have a configuration with how many? 1, 2, 3. Let me see how many balls are there. 1, 2, 3, 4, 5, 6, 7, 8. Suppose you have these 8 point masses arranged in two different configurations. So which one will have more potential energy and which one will have less potential energy? Okay. So as you can see, the potential energy of the configuration A, the magnitude will be more than B. Okay, you should not get confused with the negative sign. The negative sign is only to tell you that it is attractive in nature. Okay, so this has a higher configuration of the potential energy as compared to B. So when it is becoming smaller and smaller, then it has more potential energy. Now let us look at the case for a spherical cloud, because a spherical cloud, you can think of many point masses which are arranged in a certain way. So you can have a spherical mass distribution. Now for potential energy for 2 point masses, we calculated GAU equal to minus gm1 m2 by r. So this is a continuous mass distribution. This is not discrete mass distribution. So for this continuous mass distribution also you can calculate potential energy, similar to the way one can calculate the potential energy for an electrostatic charge distribution, where the charges could be discrete, or it could also be a continuous charge distribution and you are asked to calculate. Then you will actually take a slice, a disk, and put one test charge outside and see how much is the potential energy, and then integrate over the entire circle, entire sphere. Similarly, you can do exactly the similar thing for the gravitational case also, where you take a test mass outside. You can consider a sphere, you can consider a disk, potential energy of the test mass with the disk, and then you can integrate. So when you do this for a spherical mass, the potential energy of the spherical mass distribution, you can calculate it, and it comes out to be minus 3 by 5 g m square by r. So this can also be calculated. In fact, this is an assignment. You can calculate what is the potential energy of a spherical mass distribution. Now it has a negative sign, which means that this the effect of the potential energy, that it is attractive in nature. That's why you are getting a negative sign here. The force is attractive in nature. Now, in a spherical cloud of gas, it's not enough to just consider talk of the potential energy due to the gravitation. There is also, because it is all made up of many small particles, these particles, which you can think of them gas, dust, whatever you want, but mostly gas, right? Because dust is very small. So in our simplistic considerations here, we will consider it to be made up of just hydrogen. Okay, you can also put in helium and so on in the right ratios. That is a trivial addition. But for a simplicity, let us consist of the spherical mass of gas made up of only hydrogen atoms. Now, if atoms or molecules, it's up to you. So once it is made up of this, it's not enough to just consider for this entire mass the effect of the gravitation. It is also important to consider that these particles will be moving because of the effect of certain thermal energy that the cloud may have, because the interstellar medium also is at a certain temperature, correct? And this temperature, because of this temperature, the particles will be constantly moving, because how do we define temperature? You generally at very lower when you are learning introduced to temperature, we define it as degree of hotness, coldness. But as you start learning more and more, you understand it is degree of hotness, coldness with how we feel. But there is a more crisp definition, and that is related to the kinetic energy of the particles involved in the system. So it's the average kinetic energy of particles in the system is the temperature of the system. So the temperature of the system can be related to the internal energy of this cloud, or in this case I will call it kinetic energy just for simplicity, or you can call it internal energy. Now that is given by 3 by 2 kT, you know that if you have a single particle, because of the 3 degrees of freedom, the energy the thermal energy is given by 3/2 kT. And if you have n such particles in this cloud, then it is given by 3/2 n kT. Okay, there are n particles. Now, how do I determine n? Is it possible for me to determine how many particles are there in here? Yes, if you know the mass of the cloud. So I can write this expression in terms of the mass. How? The mass of the cloud divided by mass of each particle. In this case, I'm considering a mass of each particle to be hydrogen atom. So mass of cloud divided by mass of each particle will give me the number of particles in this cloud. So therefore, the kinetic energy or internal energy is given by 3/2 kT times capital M, the mass of the cloud, by the mass of the hydrogen atom. And as we have already seen, what is temperature? Temperature means the average speed, okay, average kinetic energy of the particles. Okay, so that is how it is related, and that is how we have got the thermal energy of the particle. Now, for a star to form, it is important that this cloud undergoes self collapse, correct? Because it has to have very high pressure density for the fusion to initiate, right? So it has to come to very high densities. And right now I told you interstellar medium is very low density. So something has to happen because of which it starts undergoing collapse. And to understand this concept, we look at these two processes. This is the most simplistic case where I'm going to look at the thermal energy and I'm going to look at the gravity. In a more realistic case, I need to consider other effects of magnetic field, effect of rotation, effect of turbulence, but I'm not going into those details. I'll just look at the energy of the cloud because of gravitation, because of gravitation and because of the thermal effects. So if now I know that the potential energy I can write in this form, 3/5 gm square by r, and the kinetic energy I can write in this form. Now the reason why I have written like this is because this term tries to collapse the gas, right? Whereas what is the effect of this term? This term is very random, right? It will, if you give more kinetic energy, as you increase the temperature to the system, what is going to happen? It is going to expand, right? So it acts, these two act in the opposite direction. That's why the signs are opposite. Okay, so here the mass can also be written in terms of number density of particles if you know the radius. That is also a possibility. So ultimately what happens is the energy of the system is dominated by these two. Okay, and whether the collapse will begin or not is decided by whether it can whether the gravitational collapse, that term is stronger. If that term is stronger, then the collapse can be initiated. The cloud can undergo collapse due to gravitation if that second term is stronger than this term. There are various things that go in. I'm just giving you the most simplistic consideration. So if this term is bigger, is larger, what happens? It will tend to collapse. If this term is larger, it will tend to expand out. So the initial collapse of the star happens, gravitational collapse of the star. Usually it is triggered by something. There may be a quasi-stable gas, a cloud of gas. Because of some triggering, it will initiate the collapse. This is what we as astronomers think. And as we have seen earlier, that there is this eternal battle between gravity and thermal pressure. That is there not only during the make sequence phase, even during the star formation phase. Okay. But in star formation phase, the other factors can also be more important, like magnetic field, rotation, and so on. So that is what decides. Now, because of this self-gravity, the star can start undergoing collapse. But when it starts undergoing collapse, it is not that you have one homogeneous cloud, as I've said. There may be density inhomogeneities or small higher density, small coarse clumps within a molecular cloud, and they then by themselves can start undergoing collapse. Okay, these are cloud fragments, and as it undergoes collapse, okay, if you want to see the sequence of steps leading to the formation of star, I will tell it in a few simple steps. That once it starts to undergo collapse, what happens at the center? the gravitational potential energy is converted to thermal energy, and then the temperature rises. The pressure also is, the density is increasing, right? So the pressure is also larger. Now, this is happening. Initially, the temperature rises. So initially, the molecular cloud was made up of molecules. Then as the temperature rises, the molecules are dissociated. Okay, at the core. Outside, there is still a density gradient. So outside, things will be happening more slowly than what is happening in the core. Correct? So in the core, you will have, as the temperature rises, molecules will become atoms. Over time, as it further undergoes collapse, the atoms will become, as I'm mostly hydrogen, the atoms will become protons. Hydrogen atoms will get ionized and become protons and electrons. Okay. Before this, the temperature would have reached, the dust would anyway have been destroyed. That's why I'm looking at only gas now. Now you have these plasma of electrons, protons at the very core. Correct. Now, if the conditions are high enough, if the temperature is high enough, if the mass is sufficient, that the temperature and density becomes high enough, then the protons can be fused together to start forming helium nuclei. When this process starts, we say the star is formed. Before that, when it is just collapsing or tending to reach towards these phases, it is not yet formed a star, then it is known as a protostar. Okay, so this is in essence how the star formation roughly proceeds. You have a molecular cloud, and within that you can have the cloud fragments which individually may undergo collapse, leading to the formation of not one single star but many protostars. Okay, in the HR diagram, this is before the main sequence. How is the evolution? Now you will say, I want to understand in the HR diagram how the evolution goes. Okay, so we know that when you have the molecular cloud, it is very cold, right? And what's the luminosity? It is hardly radiating. So the luminosity is very less. It is very cold. So in the HR diagram, it will really light to the bottom right, because this is the region where the temperature is very, very low and luminosity is very less. As it starts contracting, then the temperature rises. Because temperature rises, energy increases, right? So it has to give off this energy. It has to get it transferred outside. So this energy is being given off, and it seems to shine, but it's much lower than what stars you would see. So a molecular cloud can also shine because of this energy being released. And if one sees the evolution, this is how it will seem to evolve. Over time, because it is collapsing, the temperature is rising, the luminosity is increasing, because the energy which is being generated because of gravitational potential energy getting converted to thermal energy, not nuclear fusion, that is being released from the surface. So it seems to have some luminosity, and over time the luminosity increases, temperature increases of the protostar itself. Okay, this is where, for example, the protostar is assembling from a collapsing cloud fragment, and then it heats up, and this is where it leads to and it undergoes various processes. I'm not going into those details of the processes, but at some stage it forms a main sequence star. So once it forms the main sequence stars, it will settle on this point. So it is the same star which has traveled all the HR diagram, and now it is sitting here. And it will sit here for as long as it is in the main sequence phase, because in the main sequence phase, the temperature and luminosity hardly change. There is a very small change. It is not that one star can become a massive star or become a Loma star, main sequence star. That is not possible unless some other star is involved and so on. But if it is an isolate, let us say it is not influenced by any other stars around, then it stays in the main sequence phase for phase in this point in the HR diagram, or very close to this point, as long as it is in the main sequence phase. Now the stars of the objects of different masses, they form stars of different masses, and it so happens that if you are forming a massive stars, then the whole pre-main sequence collapse happens on much faster time scales to form the massive stars. Why? Because there's a lot of mass involved. So it undergoes the collapse and other processes on a much faster time scale as compared to the low mass stars. So for example, a 15 solar mass star, for it to reach to the main sequence phase, it takes around 60,000 years. On the other hand, let us look at the sun. For the sun to reach the main sequence phase, it takes about 50 million years for the cloud to get assembled, go through these various processes and reach the main sequence phase. So if we look at even lower mass star, like the half the mass of the sun, then it takes 150 million years. Now look at 3 times the mass of the sun, it is 3 million years. Around 9 times the mass of the sun, it's around 150,000 years. And if you take 15 solar mass stars, it's 60,000 years. So you see, you get an idea that it takes very short time scales for massive stars to form. The pre-main sequence evolution time scales are much shorter than for the low mass stars case. And again, this is all related to the physics that is happening within the interstellar medium and the collapsing core. Okay, so I will stop with this for today, and I will take any questions that you may have. Yeah, I'm just checking for the questions. Give me a moment. Okay, so there is a question: why are absorption lines more concentrated towards the left side or the lower wavelength? Okay, so this has to do with the way the distribution is in terms of energy, because ultimately the wavelength of the absorption line is related to the energies. So how it depends on the species of consideration, and it depends on how the energy levels are distributed. Okay, so that has to do with quantum mechanics, why, how the distribution or how the quantization of energy levels happens. Okay, so depending on the species, you will see that the energy levels, for example, even you can take the simplest example of hydrogen atom. Okay, you can see the energy levels. Now just energy level distribution is not enough. You have to see also whether energies of how many energies are there toward, how many energy levels are there towards the lower side vis-a-vis how many energy levels are there towards the longer wavelength side. And you also have to see how many photons are being able to be provided at these different energies. So you need to take these two factors into consideration in order to understand this. Okay. Okay, is Betelgeuse an M-type star? I heard it is a red supergiant. So does it mean it is smaller or larger than the sun? So I hope that question has been answered during the course of the lecture. Okay, so it is a giant star. It's a supergiant star. Okay. Can we use the observatory present in IIST to plot the spectrum of stars across all the wavelengths, or only invisible? See, in IIST, we have an observatory, and in this observatory we have a telescope, and in this telescope we have we have a CCD, but we also have a spectrometer. But this spectrometer functions only in the optical wavelength. If you want to do measurements in ultraviolet, you really need to go to space. Okay, and if you want to do measurements in infrared, at IST we don't have, only the large observatories in India. Ours is a very small observatory. They have an 8-inch telescope and a 14-inch telescope. You really need to go to, for example, the Hanle Himalayan Chandra telescope at Hanle, for example, to be able to do measurements at infrared wavelengths, because you need to have an infrared spectrometer, and infrared spectrometer needs to be built, and that is not something that you can very easily buy off shelf. Whereas an optical spectrometer, small one to work with small telescopes, are available off shelf. You can buy them from companies. But infrared, you have to build your own telescope suited, own instrument suited to your own telescope. Okay, so at IIST we have only the infrared case. Okay, what is V in B9V? I think this is also cleared. Can you explain measurement of luminosity? So how do we measure luminosity? Okay, so as I told you, when we are doing this kind of measurements, you can, if you're plotting the HR diagram, if this is in context of HR diagram, I can tell you what it is. In the HR diagram, you can plot the absolute magnitude in the V band alone. Absolute magnitude in the V band, that means you're measuring the flux density through the V band itself, And if you know the distance, then you can relate to the total luminosity by some correction factors. I have not gone into those details, but let us take it. If you're measuring the flux density in one band or across the full spectrum, then you can get the luminosity if you know the distance to a star, because luminosity is equal to 4 pi d square, distance to star, multiplied with the flux density. So if you are measuring the flux density in the V band, you get the luminosity in V band. But using models, we can relate luminosity in V band to the total luminosity of the star for main sequence phases. Okay. Are all stars capable of ionizing hydrogen atom? Now, this is a very interesting question, and I want you to answer this because you should be able to see what kind of radiation will ionize hydrogen atom. Can hydrogen atom be ionized by radiation of a temperature equivalent to 3000 Kelvin? So what you should do is you should see where the, for example, surface temperature is of the star, and you should see that the temperature corresponding to this surface temperature, the wavelength corresponding to this surface temperature using the Wien's law. And for that wavelength or frequency, you calculate the energy of the photons, because most of the photons will be of that frequency or that wavelength corresponding to the peak. Correct? Now, that energy, once you know, you see whether that is enough to ionize hydrogen or not. So hydrogen, for example, can be ionized if you have photons of energy greater than 13.6 eV. And it so happens that if you see the spectral classes of O and B stars are capable of ionizing hydrogen because they give off a lot of radiation in the UV. Okay, but the other stars can ionize maybe a very little bit around it, but not a lot. But the low mass stars is not possible. Okay. Can you explain the formation of protostars and mechanism? The very early formation of star is fully discovered. Is there any quantum gravity involved in protostar formation? We are in protostellar formation right now. We have not yet gone to the stages of quantum gravity yet, because we are still understanding protostellar formation itself. We do not understand the sequences, and broadly I have explained some of the sequence of steps which lead to the formation of protostars. Okay. And what is self-gravity? Self-gravity means if you have a large mass of gas, if there is a trigger, then it can by itself start undergoing gravity, because it can become unstable to gravity and it can start undergoing collapse. That is what leads. And we as astronomers are able to think of few triggers that can lead to probable collapse of clouds of gas to form stars. But the exact sequence of steps, like what it was before and what triggered, the thing is, it's a laboratory where we can just do observations at different stages and then try to come up with hypotheses. We cannot test as we want it, and it is possible we may not find a stage where we are seeing exactly what happened. It's happening now because we don't know the future, because all these processes take a long time. So in real time, it is not possible for us to see these processes, the triggering, the collapse. We are able to build up our knowledge and our information because of observing many different star forming regions. Okay. What is the difference between giants and supergiants? Is the size the only parameter? Yes. In the HR diagram, size is the only parameter for size, and luminosity, of course, is the only parameter for classification. In the luminosity classes, it's just that. But internally, as we have seen, the supergiants are formed only from the massive stars, whereas the giants can be formed from the low mass stars. That we will see as we move along. Okay, the future of sun jumps to red giant and suddenly drops to white dwarf. Why? Okay, it doesn't happen that way. It actually goes through a lot of intermediate phases, and we are going to talk about this soon. The reason why I just told about this, because these are two kind of extreme phases which you can see, and the star spends quite some time in these phases. That's why you can see them. But the intermediate phases are of shorter time duration, so you don't see them as often, but they are there, and we will be talking about them, and we will be seeing in the HR diagram how the sun travels through the red giant phase. It doesn't jump, it actually travels through and comes to the white dwarf phase. So we will be talking about this in the probably in the next class when you're talking about evolution of stars. Okay, is it due to lack of fuel in the end and due to gravity? Okay, all these are related to evolution of stars. We will be talking about them in the next class. Why Sirius star is bigger and brighter? It is brighter. It is not bigger. It looks bigger because it is brighter. And you know, ultimately, brightness depends on the distance to star, as we have seen. It is brighter than other stars because of various factors. Its internal luminosity combined with distance effect. These two factors play an important role in telling us how any star will look like. So it so happens that in the night sky, the distance and internal luminosity of Sirius A is such that it is appears very bright to us, brighter than all the other stars. Okay, what about gamma burst? We didn't talk about this, so I'm not going to answer that. How do G, K, and M stars lead to giant and supergiant? So I think there is some confusion here. It doesn't mean that GKM can be only in main sequence stars. GKM can be also in giant stars, supergiant stars. Any star can be a G type or K type or temp type depending on its surface temperature. So the surface temperature decides whether it is G or K or M, and that can be a giant star, it can be a main sequence star. So I hope this is clear now. That when I said GKM type, it doesn't mean GKM main sequence stars lead to this type of stars. Essentially, it means that giant stars and supergiant stars are found to have effective temperature that correspond to spectral type of G, K, and M. In that temperature range, its effective temperature lies. Okay. Interstellar medium is there due or while forming galaxy, collapse of first generation of stars due to gravitational collapse, stars formed, and then planets as well. Yes, even due to when galaxy was being formed, you needed to have interstellar medium, correct? Because interstellar medium is there in our galaxy. Between stars means in our galaxy it is there. So it was there because from that interstellar medium only the first generation stars also formed. But there is a slight difference. The first generation stars had hardly any metals. They would not have any metals because at the time stellar processing was not there. But over later time, as more and more stars the metals formed in the center and it was given mixed with the interstellar medium. So the later generation of stars will have these lines corresponding to the metals. The earliest generation stars, in all probability, many of them, for example, the massive ones would have evolved off. And another interesting thing that has been brought up because of this question is the fact that there are astronomers and groups who are really interested in understanding how these first generation stars look like, because due to the absence of metals, the stellar processing, the way the energy gets transferred, the energy transfer mechanisms and the physical processes in the interior of stars could be very different. Metals play, even though very tiny amount, metals play a very important role in all these processes. So it is thought that the first generation stars were much more massive, okay, and much more luminous than what they are now. But to understand that, one needs to understand the role of metals. I'm not going into those details, but since it has come up, I just want to make it a point that those stars did not have metals, and we believe that therefore they were different from what the stars that we see now are. Okay, can we find the interstellar medium in abundance in some parts, or is they present everywhere? If it is everywhere, where are they present in our solar system? Okay, in solar system, we don't talk of interstellar medium, we talk of interplanetary medium, because in the solar system, it's all related to the sun. So when we are talking about interstellar medium, it's between stars. So if you go out of the solar system, you will encounter interstellar medium. In fact, I urge you, there are these two Voyager missions which were sent out by NASA in 1970s, and one of them has moved into the interstellar medium. Okay, it has gone out of the solar system. You please go and check about the Voyager missions, and you will understand that in at least one of them we have moved out of the solar system into the interstellar medium. We have not, it takes a lot of time to reach even the nearest star, so we are in the interstellar medium in one of them, one of the Voyager missions. Okay, can the interstellar dust be formed after any astronomical events like supernova? It's very unlikely, because for this you need certain conditions. Okay, and you need the right conditions for dust to form. In case of supernova, it's a very violent explosion over a very small period of time in which a tremendous amount of energy is given off. The amount of energy that is given off in the supernova is so large, forget about dust. The dust anyway will, for example, close to the supernova formation is impossible. If there's dust close by, it will get it will get sublimated, ionized, and or it will have a lot of energy within that. The matter there will be such high energy that it emits in X-rays, very, very high temperatures. Okay, so it is dust cannot form during supernova events. Okay, somebody is talking about type 1a supernova. I have not talked about that, so I will not discuss that. Okay, I think I have covered all the questions that were there. I think most of them which were sent to me. So that is all for today, and I hope you enjoyed the class. So we will meet next time to see about a little bit about star formation and main sequence stars and stellar evolution. Okay, all right then. Bye bye, and see you.